Einstein condensates.
All right. Okay, let's see. Can you guys see my tiny cursor moving? It's under turbulent right now.
Yes, I can see that.
Super. Alrighty. So thanks everyone for coming to my seminar. And indeed, I'll be talking about turbulence in atomic Bose-Einstein condensates. And the real hero of this story is Ming-Shu Zhao, who is now applying for permanent positions in China. I'd like to start by begin by saying that this is actually the first time I've given a seminar length presentation on this material. So we'll see how timing goes. Secondly, particularly for the parts of this that's outside of atomic physics, many of you may know pertinent references even better than me. So after this talk, if I've neglected some reference that's really important, please share it with me. I even have a notepad here so I can write these things down. So I would really like any kind of input of that type. All right, so with that said, yes, I'm at NIST and the Joint Quantum Institute in Maryland. The top three projects here are things that are sort of being supervised by myself, and then the bottom three are collaborative projects with the boxed senior colleagues on the bottom. So one of the great things about the JQI is our ability to really collaborate with a wide range of senior colleagues. So with that, this is sort of I don't know, a menagerie, I guess, of recent projects to indicate the diversity of things that I'm kind of interested in. So with Steve Eckel and Gretchen Campbell, we've been looking at cosmological analogies you can do with cold atoms. So this is an experiment looking at expanding and contracting ring-shaped BECs with some analogy to cosmology. The same lab I'll be talking about today looked at superfluid densities in anisotropic BECs. We have something coming out really, well, going to be in the archive really soon about imaginary gauge fields related to the Hitano-Nelson model of condensed matter physics. Sort of two related projects, both with theory in the bottom and experiment on the top, using weak measurement to discern time-separated correlation functions, of which the dynamical structure factor is one example. And in a different lab, but actually with Gretchen and Steve again, we've observed the Rayleigh-Taylor effect recently, and that's on the archive. And sort of in the vein of uh, sort of entanglement transitions in time, I have some theory work with my colleague Hilary Hurst. So with that out of the way, these are our champions. So this is project is really Ming-Shu's baby. Since he started graduate school, the thing he wanted to do more than anything else is do hydrodynamics with BECs. So he came again and again and again with ideas about how to do this. And finally, what I described today, his idea was to form the nucleus of this. And then his lab partner was Junheng Tao, who's now a postdoc at Harvard. Alrighty, so we'll be thinking about turbulence. And obviously, this is sort of conceptualized by beautiful pictures from Leonardo da Vinci, indicating the sort of chaotic pattern of fluid flow that he would observe as water emptied into a basin. And we're going to be thinking about analogous behavior in atomic BECs. The picture on the right is a simulation using the 2D GPE of our disk-shaped BEC. And I'm going to really try to be clear about what's the same and different for turbulence in this quantum system compared to different classical systems. And the first thing that's very different are the physical scales at which we'll be looking for turbulence. So our Bose-Einstein condensate is ultra cold, it's ultra dilute, it is a compressible fluid, and it kind of has zero viscosity. Now, viscosity is a bit of an interesting question, but certainly it's a superfluid. Superfluid helium-3 is, or helium-4, excuse me, is much warmer. It's much denser. It is incompressible and is also superfluid. Air is less dense than helium, more dense than a BEC. It's compressible and it has viscosity. And similarly, water is an incompressible a viscous fluid. So one of the important questions is what is the relationship between turbulence and these kinds of fluid systems? So for the purpose of this talk, air is a fluid as well. It's just a compressible fluid. All right. So for me, as an atomic physicist, I needed a primer on hydrodynamics. So I have a two-slide primer on hydrodynamics here. So we'll start with compressible fluids. Well, typically you think about conservation laws. So the continuity equation is expressed in the conservation of mass. And the Navier-Stokes equations is expressed in the conservation of momentum and contains a viscosity term. And we'll come back to the connection of these specifically with our experiment in a couple of slides. Incompressible fluids drop some of these terms. So there's no density change, and correspondingly, some terms have vanished from the conservation of momentum equation. Secondly, and importantly, for a classical fluid, there is no particular constraint on the vorticity of the fluid. Whereas for superfluid flow, the vorticity has to be zero except at the location of quantized vortices, right? So this will be potentially a difference. And with that said, let's try to understand how I would like to think about fluid dynamics in atomic BECs. So for starters, our atomic BEC consists of just a single hyperfine state. So in a sense, it's a scalar field. We'll characterize a scalar field by the mean field wave function psi, which evolves according to the Gross-Pitaevskii equation at very low temperatures. Let's see. So it's a nonlinear Schrodinger-like equation with an interaction term here that's proportional to the density of the atom psi squared. It's convenient to convert to hydrodynamic variables, meaning we're going to express the wave function psi in terms of the square root of its density times the exponential of a phase. The density in mass terms, because we're actually thinking about hydrodynamics, is related to the square of this field, and the velocity is related to the gradient of the phase. Because the velocity comes from a phase gradient, we know the fluid is irrotational. So this then is the first profound distinction between this fluid and a classical fluid. We can derive a continuity equation from this expression, from the conservation of probability. And this is telling us that we're working with a compressible fluid, not an incompressible fluid. And the remaining term gives the quantity analogous to the momentum conservation expression. The first term in the gradient results from interactions. The second term results from what's called quantum pressure. It's simply part of the kinetic energy that can't be organized in any other way. And then the last term comes from the external force. And the thing I want you to take away, notice, is this is virtually identical to the Navier-Stokes equation. All right. In particular, if the quantum pressure term is zero and you have a zero viscosity fluid. Okay. Great. So other groups have looked at turbulence in Bose-Einstein condensates before. We are certainly not the first to be interested in investigating this phenomena. And I'd like to sort of organize this information for you to the best of my knowledge and to give context for where our experiment is entering. So firstly, these are all time-of-flight observations, which means somehow you had a trap of cold atoms and you dropped it, and after it fell for a while, a picture was taken. And two kinds of information might come out of such images. If interactions are strongly important during time of flight, pictures such as this, after time of flight, have a lot to do with the dynamics of the interacting expanding gas, as was visualized here with a tangle of vortices on the inside of it. And so this is perhaps the first paper looking at quantum turbulence or turbulence in a BEC. One of the big pieces of evidence that these authors present that this is turbulence is the fact that the expansion of the cloud during time of flight is dramatically different whether or not they stirred it up to make a turbulent state. When it was turbulent, the size of the cloud essentially didn't change, or the aspect ratio anyway didn't change, indicating the vortices are somehow binding it together. This is their interpretation. Whereas a regular expanding BEC has an interaction-driven inversion of the aspect ratio. So this physics means it is strongly dominated by interactions in time of flight. On the other hand, experiments can be performed in which interactions are not important in time of flight, and I'm featuring data from Zoran Hazababik's group, in which case the information in time of flight is telling you about the momentum distribution. This is useful because the momentum distribution, or more specifically the energy distribution, is a quantity that is frequently predicted in Kolmogorov scaling. And I'm going to come back to the predicted scaling exponents in a little bit. But long story short, when these momentum distributions are collected over a reasonably wide range of momenta, there is at least a range from here to here in which this log-log plot looks like it's linear. So one can make a case for power law behavior, and it is this power law behavior that will be the predictions of Kolmogorov theory. All right, so this has been fruitful, and in fact, the Brazil group also has a paper where interactions were less relevant, and they see a similar scaling behavior. All right. However, if you come from the perspective of classical fluid dynamics, it is not traditional to characterize turbulence using momentum distributions. In fact, when cold atoms first came on the scene, one of the novelties of the system is it is easy to measure momentum distribution. But this is not what is measured in typical classical systems. Rather, in classical systems, the technique of particle image velocimetry, PIV, which is what I'll call it, is used instead. And the basic idea is to place some kind of tracer particles inside your fluid and to rapidly image the position of these tracers in such a way to obtain a position resolved map of the velocity field of this fluid. All right, so the idea here is that there's some underlying velocity field. One first notices the position of the tracers at time equals 0, then allows a system to evolve for some time and measures where the tracers have evolved to. And as long as this displacement is fairly small, one can deduce the velocity field. So this type of measurement is supernatural in classical fluids, but it's a challenge for cold atoms. It requires us to have tracers in the first place, and then it requires knowledge of the difference in position from when the tracer started to where it ended. So I will be telling you how we perform these kind of experiments in our system. With that information, classical fluid dynamicists try to describe turbulence. So the first thing I want to point out is that Kolmogorov theory, as I'll be describing it, is actually valid only for incompressible fluids. So for compressible fluids like ours or water or something like that, Kolmogorov theory is not strictly valid. The tradition is to use something called a far average, or just a density-weighted average of the velocity field, and associate that quantity with the V's that would come from a incompressible fluid. All right, so we see that this is the actual velocity field weighted by the local density divided by the density. And in everything that follows, I'll be dropping the tildes, but just keep in mind that we will be working with compressible fluids and extracting quantities in this far averaged way. All right. All right, so once you have a velocity field, it's traditional to express the spatial structure of this in terms of velocity increments, which is saying what is the velocity difference um, relating two positions separated by L. So if position X and position X prime, what's the difference in velocities? That'll be a velocity increment. And then one expresses the statistical properties of these quantities in terms of velocity structure functions. These can be longitudinal, transverse, or scalar. And let me unpack a little bit what this is about. So this S is S of P, has an L and T, or it could have an S. It's a function of L. So what are we doing here? We are taking the velocity increment for some separation L at a position X, and we're taking the inner product of that with a unit vector. Now, this unit vector could either be parallel or perpendicular to the separation variable or vector between these two points. So we're projecting the velocity increment either onto or perpendicular to the unit vector aligned along the difference vector between these things. Okay, so this is a rather convoluted thing, but where it's either transverse velocity differences or longitudinal velocity differences. We're then taking the absolute value of that and raising it to the pth power. So this then would be the p-order structure function, either longitudinal or transverse, and if it was scalar, there would be no inner product. These wedges indicate averaging over the spatial extent of the system. All right, so it's still a function of separation, but is not a function of the initial coordinate. And in our experiments, there will also be an ensemble average as well. All right. The original Kolmogorov theory then predicts that the scaling of these structure functions as a function of the exponent should go as to the exponent divided by 3. There's two key ingredients that are going into this prediction. One is that whatever the velocity distribution of this system is, it's scale invariant. And secondly, there's a calculation that can be done that specifically predicts what this function is for the energy scale factor, if the something going as k squared. Okay, so this is known as the K41 theory. Now, in quantum fluids, experiments of this type have been done. So here is an explicit measure of a transverse velocity function in superfluid helium. As is often the case in superfluid helium, the measurement is very clever. What's been done here is ionized molecular helium-2 has been installed, diatomic helium, installed into this along an initial line. And then after some evolution time, that line displaces, and that molecular ion has a transition in the near infrared that can be imaged using laser imaging techniques. So that's the tracer in helium. And what you're seeing here is a typical plot in this kind of business that's showing different order structure functions. The n is what I had called p in the previous slide, as a function of the third order structure function. Now, this is a little weird. This is called the extended self-similarity assumption, but this could just as well be plotting as a function of the interparticle spacing. And what they're doing is over some restricted regime, fitting this to a power law, and then they would plot the power law as a function of the exponent n. So that's sort of the strategy that's employed in classical fluids. So that's really what Ming-Shu was interested in. He wanted to do these kind of experiments using tracers rather than momentum distributions in atomic BECs. So what I'm going to try to tell you in the remainder of the talk is how we do velocity measurements in rubidium-87 BECs, the relationship in more detail between these measurements and turbulence, and how we observe Kolmogorov scaling in this system. All right, so let's begin by thinking about tracers. What are our tracers going to be? Well, we can't just install a ping pong ball in our system. It would weigh way more than it and just evaporate the BEC away. So what we're going to use is another hyperfine state of the same atom as tracer particles. It's roughly similar as to using the molecular ions in the helium case. It's something that's already there. Now, we're working in the F=1 manifold of rubidium-87. Our bulk gas is in the MF=+1 state, and we're going to use the MF=0 state as our tracer particles. Now, for this to work out, whatever tracer particles we instantiate have to be interacted very similarly with themselves as with the other atoms. And in fact, in the GPE sense, this is parameterized by interaction constants that we'll call 1, 1, 1, 2, and 2, 2. And in rubidium-87, it so happens that the self-interaction, the cross-interaction, and the alternate strength interaction are all within about 0.5% of each other. So this is a nearly isotropically interacting gas. What that means is that even if you put in a bunch of tracer particles, they would flow exactly in tandem with the original fluid and not modify the flow pattern much at all. Okay. Now, technically speaking, in the laboratory, we could imagine creating such tracers using a pulse of radio frequency radiation. But unfortunately, the radio frequency radiation has a wavelength on the scale of multiple meters, and as such, we're not able to use it to pattern any particularly interesting structure. We would just sort of sprinkle everywhere inside our cloud uniformly these tracer particles. Now, this could be done perhaps by having a near-field structure like a wire nearby, but we don't have that in our laboratory. So what we need is a technique to inject tracers in a spatially dependent sort of way. And, well, what resources do we have in a cold atom lab, if not light? So we'll be using light, and the whole point is that its wavelength is comparable to but smaller than a micrometer, which is also comparable to what our imaging resolution is. So we're going to be using optical means to instantiate these tracers. And in the spirit of atomic physics, let me give you a sense of how this actually works and why it works. So we're going to be using the light shift. Now, if you go to a talk, you might hear the word light shift, you might think optical lattices, but there's more to the light shift than optical lattices. So we're going to think about the incident laser in terms of an incident optical electric field with a polarization, a wave vector, and a frequency. And if you analyze a typical atom, this will just have the electric dipole interaction will have 3 terms. A term which is often called the scalar term. This is a term that's simply proportional to the overall magnitude of the optical electric field. It's often used to create optical lattices. A second term, which is called the vector term. The vector term can be organized in such a way that it looks like a vector dotted into the vector of angular momentum operator, so it acts in much the same way as a magnetic field does in the sense of the Zeeman effect. And there's a higher order term, which is typically called the tensor light shift, but really it's the rank 2 tensor, the vector is a rank 1 tensor, and the scalar is the rank 0 tensor. Right? In particular, for our atom, if one tunes between the 2 D lines, so we have lasers either at 795 or 780 nanometers, 2/3 of the way between these 2 transitions is a magic wavelength where the scalar light shift vanishes, leaving behind only a vectoral shift and an incredibly feeble tensor shift. So this is what we do. We're going to operate our lasers at 790 nanometers where there is no scalar contribution, and all the light we're going to use is couple to the internal degrees of freedom of the atom. And this is then our handle with which we're going to be able to manipulate the internal state of these atoms. Now, what you see is that this construction requires the cross product of the polarization vector with itself to be non-zero, including a complex conjugate. Now, for linear polarization, this doesn't do anything. Instead, you need a little bit of ellipticity for this quantity to be non-zero. And in fact, we're going to use circularly polarized light to achieve this. Okay, so it is an AC effective magnetic field that behaves exactly the way an RF magnetic field does, coupling together our internal states, except now that it is spatially structurable. Now, what we do is have two tones on the same optical field, and the frequency difference between those two tones enables us to drive transitions. So in short, we can couple together the internal states with an effective time-dependent oscillating magnetic field. And in the end, our instrument looks like this. We come in with a single spatial mode of light that is circularly polarized that contains two frequencies on it. These frequencies differ by an amount equal to the linear Zeeman shift of our atom. We have a Bose-Einstein condensate that is entirely in MF equals 1 state. This laser field then hits a digital micromirror device whereby a pattern of mirrors determines the pattern of light that will be incident upon the BEC. And we briefly flash this Raman field on, doing a fraction of a pi pulse to flip the atoms in certain regions of the cloud to different hyperfine states, which we can then detect. So this then is how we instantiate tracer particles in our BEC. Okay. So I'd like to sort of now outline what an experiment looks like so that you can have a visualization of how this works. So in the first step, we prepare a Bose-Einstein condensate, which when imaged in situ looks like this. So there will not be any time of flight data presented for this experiment. So these are atoms in the initial state in a BEC. We then use this two-frequency co-propagating Raman configuration to transfer the atoms in selected regions of the cloud to this 1-0 state. We have a pattern such as this on the digital micromirror device. In a second, I'm going to tell you how we detect them. But anyway, we'll see a picture like this. So the idea is after creating a particular pattern, the atoms are in the 1-0 state. That would be this state here. The energy difference between the 1-0 state is different than the energy difference between the 1-1 and anything else state. So we use a microwave field to transfer the atoms from the F equals 1 to the F equals 2 manifolds. Why do we do this? We do this because we have an optical coupling, an optical field that we use for imaging that's resonant on the F equals 2 to some other excited state, F prime equals 3. This allows us to image only the atoms that had been projected after a two sort of step process. First, we create them with the DMD. We then perform a microwave transfer. We then image them. So of all the atoms in the BEC, we see these two little pockets of atoms that have been transferred into the 1-0 and then to the 2-0 state. We then wait a while and perform the same experiment again. And now we see that these clouds of atoms have moved. We've done this a number of different ways, but in the end, we gather statistics. And you can see there's this tiny displacement of the cloud of atoms. X is where it started, and the dot is where it went to. And this displacement will be the observable from the remainder of the talk. Now, I'm a bit of a skeptical person. And when I see these displacements that are small compared to the little tracers we created, I told Ming-Shu, I don't believe that this is working, and how can you convince me that it's working? So I want to come back to this sort of vorticity pattern of a Bose-Einstein condensate. So if you take a BEC and start it rotating, as long as it rotates sufficiently slowly, there won't be any vortices in it. But nevertheless, it will have some kind of overall angular momentum. Now, I previously said that this BEC has no local vorticity. Del cross the velocity is 0. So then what is the fluid flow pattern that has to exist in order to allow the overall cloud to rotate? Well, it's a pattern as I've plotted here, resulting from the gradient of the product of the x and y coordinates. These equal should really be proportional to, it's proportional to whatever the rotation rate is. This is very, very different than a velocity field for a typical rigid body rotating. Okay. So this has been long predicted and measured sort of in secondhand ways in cold atom systems over the years. So we said, let's go ahead and measure this. So that's what we did. We did a series of experiments where we prepared tracers located in different experiments on 3 concentric circles with diameters of 2, 5, and 10 micrometers. We repeated the experiment a number of times in a rotating system and measured the velocity field. So in particular, we're using this digital micromirror device to pattern the cloud of atoms. So the overall harmonic trap, in fact, is made with the digital micromirror device, and Mingshu commands the device to rotate. It rotates by an angle of pi/2 in 15 milliseconds, and then we image it. On the right, you'll see the predictions of the GPE, and on the left, you would indeed see a very good correspondence between the expected irrotational flow pattern and our observations. So indeed, this technique is capable of measuring, even on the inside, quite tiny displacements. So we become convinced that we have a technology now that allows us to measure velocity fields inside a BEC. Now, going forward, we're going to be looking at uniformly trapped gases. This is the only harmonically trapped gas in our data set. Everything else will be trapped in a disk with uniform density. Right. So with that, I've told you how we measure the velocity field in our atomic BECs. And now I'm going to go into a little bit more detail about turbulence in these systems. All right. So I've used the word turbulence loosely. Let's be a little bit more specific about what we're thinking about here. Typically, when you think about turbulence, the first thing you think about is the kinetic energy power spectrum. So this is saying that for a quadratically dispersing system, if we look at the Fourier transform of the velocity Vx and Vy fields, square them, this is going to be proportional to the energy as a function of Kx and Ky, or the energy density and momentum space. This is traditionally averaged over the angular variable to yield plots which in a cartoon sense look like this. So this is the classic turbulence plot that says energy is injected at some large scale. Then over time, in momentum space, energy flows from long length scales to short length scales. This intermediate regime is typically called the inertial regime, in which this power law behavior can occur. And then at some very, very long, short scale, there's some other mechanism at which energy dissipates. And because energy is conserved in the system, even in the momentum variable, there has to be an energy flow that obeys a continuity-like equation. Okay, so we expect a power law. So the original Kolmogorov fluid theory says we're going to look at local turbulence in incompressible viscid fluids at large Reynolds numbers. So it's actually quite specific. And then you're going to look at the decay of this isotropic turbulence, and you're going to assume that everything is isotropic in space. So under those assumptions and a scale invariance criteria as well, one obtains the Kolmogorov result. Let me just sort of hit the spacebar a bunch of times to finish building this in. Okay, so here are some key predictions, because you will hear the blah, blah, blah law pretty frequently. So the 2/3 law says that the prefactor of this power law has a 2/3 is energy to an epsilon energy to 2/3. So this is a dissipation rate. Then it says that the scaling is a -5/3 in momentum. And then it says all subsequent velocity structure factors, if you look their power law as a function of separation, is p divided by 3, where p is the power. So this is the original Kolmogorov theory. So it makes a strict prediction in terms of what the scaling of these velocity structure functions should be as a function of the exponent. Okay. Now again, our system is compressible. And in the simulation, you see a wide range of densities. So indeed, we have to do far averaging. Our blobs encompass a reasonably large volume of this, meaning they average significantly over the microstructure. And that's important, actually. If there are vortices present in the system, we want to be averaging over many such vortices. Okay. All right. So I want to turn back again to superfluid helium. Both aspects of this have been measured in superfluid helium. So both the momentum scaling, the 5/3 law, has been measured, and using what's called grid turbulence, this is a moving grid to induce turbulence, even the sort of 2/3 involving the dissipation rate has also been measured. So this, even for quantum fluids, seems to be applicable, but helium, superfluid helium, is still a compressible fluid. So we need to move into this, sorry, incompressible. We need to move into this compressible regime. All right. And coming back to the kind of BEC data I showed before, here are two results looking at momentum distributions in time of flight that over some range of parameters appear to give power law behavior. Now, what I'd like you to notice here is that these power laws, take them from what they are definitely not the power law that is expected by the Kolmogorov theory. The reason for this is that the kind of turbulence these authors believe they're observing is called wave turbulence, which is not at all the kind of turbulence that's being studied in Kolmogorov theory. So indeed, in this sort of a 2016 paper, Zoran's group showed quite clearly that if they look at a wave turbulence model, it gives these kind of predictions. And the GPU simulation in the box is in agreement with their data. All right, so what's missing here? What's missing here is the important impact of vortices. So lastly, I'm going to come back to the Kolmogorov description and how we're going to see this in our system. All righty. So I previously told you that the important metric is the velocity increment from which we produce velocity structure functions, from which we can define moments of the distribution. So let's go look at this. We're going to put sometimes 2, sometimes 4 probes in our system, creating initial points with a known initial separation. We're then going to measure the velocity of each of these 2 tracers, from which we can deduce a velocity increment, either longitudinal, transverse, or scalar. In our experiment in particular, we start, as I said before, with a disc-shaped BEC. We ramp on a pair of stirring rods these are focused laser beams, also imprinted with a DMD, although a different one, that locally deplete the density of atoms. We then cause them to undergo circular motion, as pictured here, in opposite directions to avoid inducing any net vorticity to the system. Then after completing such motion, we wait a while and allow the system to come into quasi-equilibrium. So in the context then of turbulence, what this is going to tell you is we're looking at a particular kind of turbulence called decay turbulence. Decay turbulence means an initial potentially turbulent configuration was created and no additional energy is being injected at long length scales. The system is allowed to relax. So this is not some kind of steady state turbulence. Okay. We then have tracers as I described before. The orange and red circles are marking both the 1 and 2 sigma uncertainties, or actually widths from a Gaussian fit of these things. And these are determining the accuracy with which any one measurement can identify the center of these and therefore infer both L as well as the velocity increment. Okay, so in our data then, Ming-Shu took an enormous amount of data. So he did 46 separate runs of the experiment, each of which had hundreds of data points. Yielding about 40,000 velocity increment vectors. So we have a very large data set with which we can derive statistics. Let me see. Okay, this is actually not coming out. As I promised, this is the first time I've done this. So this is supposed to be the slide that's next. So the left plot here is a histogram of longitudinal velocity increments. And this part of the talk is sort of the data analysis part of the talk. And this is going to come back twice because we really want to be confident about what we're saying. The black data and the black curve is a plot of what we measure if we did not stir the system. Okay, so we're going to call this our instrument response function. That is the nominal distribution of observed velocity differences that occur in an unmoving BEC. So all sources of technical and systematic error are encoded in that. In fact, the gray line is a Gaussian fit, so it would be a parabola on this log-lin plot, and this data is extremely well modeled over 2 orders of magnitude in histogram with the Gaussian. So we are highly confident this is a Gaussian distribution. When we stir the system, instead we see the red curve, which is clearly and measurably broadened. However, its width is not dramatically larger than the width of the underlying distribution. So what we do is use a linear programming technique to deconvolve the observed data from the instrument response function, which gives the blue histogram on the right. Right. For the majority of the data I'm going to show to you, I'm going to plot both analysis of the deconvolved and undeconvolved data to give a sense of what the impact of the deconvolution is. And if you have personally ever deconvolved anything, you should treat deconvolved data with a degree of skepticism anyways. All right, so now back to this one. So using those histograms, we can compute moments of the distribution. And that's all these structure functions are, as moments of this distribution at different orders. So for example, if we construct the second moment of the distribution, we see curves of the type that's plotted on the right for scalar, transverse, and longitudinal distributions. Red is coming from the measured distribution function, and blue is from the deconvolved distribution. The curve that's plotted with this is from the expected power law of 2/3 for the S2 distribution. So we see that whether or not we deconvolve it, the 2/3 prediction is reasonably good. So this is a fit, but the fit is having a constrained power law. Now we did this one. A second property of these distributions I'd like to call your attention to is the fact that the distributions have a fairly fat tail, meaning that they are not well modeled by a Gaussian. One way to parameterize this lack of Gaussian behavior in the wings is with what's called the excess kurtosis. And indeed, if we plot the excess kurtosis as a function of the separation between quantities, we see that for the instrument response function, there is no observable excess kurtosis. And for the undeconvolved data, there is some. And for the deconvolved data, there is significant excess kurtosis. And both for the longitudinal and transverse data. Okay. One feature that is a surprise to us is that in the Kolmogorov extended description, all of these things should have a particular scaling. And what we observe, and I'll show you later in simulations as well, that the transverse quantity seems to be independent of the separation between tracers. So this is one of the unknowns in this modeling. So the structure in the wings in the fluid dynamics community is known as intermittency. And it's saying that for objects very far apart, the distribution is likely to be Gaussian. But as they move closer together, additional structure, this non-Gaussian behavior, can appear at the tails. So we have a scale-dependent probability distribution function, and that violates one of the original assumptions of the Kolmogorov theory, which is that there would be a scale-independent distribution function. There we go. So we can understand this in terms of higher order structure functions. So our nominal data analysis procedure mimics exactly what was done in the helium case I described before. We now compute higher order structure functions, and we do not use an extended self-similarity model, and we simply plot them as a function of the interparticle spacing. And each of these we separately fit to a power law function. And B is plotting the result of this fits both with and without the deconvolution correction. And the deconvolved data in particular follows exactly what we would be expecting from the Kolmogorov description, namely that the third order structure function, which is exactly calculated, has no intermittency correction, which would yield zero in this plot, and the remainder of these objects do include an intermittency correction. And I should have said that the thing that's being plotted here is the fitted exponent minus the prediction of the original K41 theory. So the scale invariant hypothesis would have everything be zero in this plot. So neither our convolved nor deconvolved data is consistent with the scale invariant probability distribution function. Kolmogorov theory predicts specifically that this intermittency correction have a polynomial form of p times p minus 3, which is saying that the zero order structure function, which is simply an expression of normalization, is zero. And the third order structure function also has no intermittency correction because this also can be exactly calculated. The prefactor in front of this expression is a priori unknown. It's different for different physical systems, and our fit to the deconvolved data yields a particular number. I'll get to that number momentarily. Now, this is for the experimentalists and anyone who's skeptical of data analysis. So our model specifically is for these fits is plotted up here. So it's a power law. Each one of these curves has two unknowns. It has a unknown amplitude and an unknown exponent. When we fit these things, we had 14 free parameters. And if you believe our uncertainties, that we spend a great deal of time quantifying, but nonetheless, if you believe them, the reduced chi-square of this is 0.6, which indicates a degree of overfitting. What I've plotted here are the amplitudes from these fits along with the uncertainties and the exponents, which I plotted in the previous slide. The dashed lines we're going to come back to momentarily. So being skeptical people, we said, let's try to make a simpler model that describes this. And if you assume that the probability distribution function has a nominal scale invariant character of a stretched exponent variety, but scale invariant, one arrives at a prediction for what these structure functions should look like, which is here, which is independent of the order as is expected for these scale invariant objects. We then add in an intermittency correction term here, which encapsulates the expected Kolmogorov intermittency and an empirical term, which would converge the Kolmogorov term if this P naught is large. We then globally fit the entire data set to this 4-parameter model, and you'll get the outcomes, which are the dashed lines on these curves. Following this analysis, the reduced chi-squared is 0.9, which is then a pretty good modeling. And this also allows us to introduce one new idea, which is a generalized data collapse model, where because each of these are power laws, each one can have a 2-parameter scaling applied to it, yielding the data collapse on the plot here on the right. So we are quite confident with our data analysis that we are not making up false data. Incidentally, if we went to larger P's, larger exponents, these error bars get really big, really fast, and that becomes unreliable data. Okay, so with that, we did some numerics as well. Inspired by the literature, we performed a dissipative GPE simulation that adds a essentially ad hoc dissipation term to the Gross-Pitaevskii equation that introduces dissipation above a cutoff. Now, in our systems, we do have a physical cutoff, which is the energy above which evaporation occurs, but there's an additional completely empirical dissipation rate. We follow this modeling procedure. We introduce a dissipation rate that makes the simulations most consistent with experiment and obtain these results. So this is equivalent to the plot I showed you before. So this shows that in a reasonable range of parameters, we see the expected behavior for the S2 quantities for scalar, transverse, and longitudinal. We see the expected type of intermittency correction observed experimentally, and the excess kurtosis follows the same qualitative behavior. Quantitatively, the scale factors between these are not the same as what's observed experimentally, and that's plotted in the sort of chart down here. So even fine-tuning this K-naught parameter didn't allow us to have quantitative agreement. Each of these quantities you'll see has about a factor of 2 difference from experimental observation. So this model is not the end of the story, but it shows that our system, in fact, is expected to exhibit this kind of turbulence. And with is expected, I'd like to turn back to what was expected. So as usual, 2-dimensional systems can be special. And it is conventional, it's conventional belief that in 2D systems, one is not expecting a direct energy cascade. Instead, one would be expecting an inverse energy cascade and a forward entropy cascade. Now, this is not a term that I had been familiar with as a cold atom physicist. This quantity Z is the integrated square of the vorticity. So it's kind of like an energy associated with the rotationality of the system. And this quantity is expected to undergo a direct cascade, whilst the energy undergoes a inverse cascade. This is a very common behavior in 2D compressible fluids, although there are examples such as soap film turbulence for which it is not necessarily the case. But this actually occurs in atomic 2D systems as well, this sort of inverse cascade. So what I'm plotting are 2 experiments from a couple years ago that looked at what are called Onsager vortex clusters in 2D BECs. And the basic idea of both of these experiments is that in a 2D system, vortices of the same sign tend to cluster together, which is really weird because that's a high energy state. So the system is moving towards highly ordered high energy states. And in their own way, both of these experiments observe that. So for example, B and C are showing, in this result, these Onsager vortex clusters. And this is a manifestation of this inverse cascade of energy in the system. Okay, so yet I tell you I'm expecting regular Kolmogorov physics and a direct cascade. So what's missing here? What's missing is that this picture requires a conservation of this quantity entropy. And our system does not have a conservation of this quantity. In fact, because our vorticity comes in the form of quantized vortices, this quantity essentially counts the number of vortices, not the sum of the sign, just the number of vortices. And in most cases, vortex number is not conserved. So the experiments I just showed you actually worked really hard to be in a regime where vortex number is approximately conserved. And in our simulations, as well as the simulations which inspired us, we very clearly see that neither the integrated vorticity nor the vortex number is conserved in our system. So because of this lack of conservation, there isn't really a cascade for entropy, and there is expected to be a direct cascade for energy. Now, I want to emphasize that we did not observe the energy flow. We simply have a system that we expect to have a direct cascade, and our observations are consistent with the conventional Kolmogorov picture. So with that, I'd like to summarize. We've demonstrated a technique to do cold atom particle imaging velocimetry, from which we derive probability distribution functions for velocity increments, and we observe Kolmogorov scaling with the intermittency correction. And we have numerical support that this is what we expect to observe, although again, I highlight there's a factor of 2 difference between the numerical calculations, even including the ability to tune a otherwise ad hoc parameter. And with that, I'd like to thank you very much for your time.
Thank you very much. So we have a bit of time for questions. I might start with one since I'm in control here. You've got this really nice probability distribution function plot, but I'm noticing that it's got this asymmetry to it. Do you know what the origin of that is?
That is a great question. And first, the answer is no, we don't know what the origin of it is. But it's useful to think about what that's telling you. What that's telling you, this is a longitudinal distribution. This is telling you that along the direction that separates the two test particles, the velocity going away from you is different than the velocity going towards you. And there is no reason to expect this quantity to be symmetric. When things are very close together, in fact, you would expect on average things to be flowing away more than they're flowing together to avoid an accumulation of local density. Okay. So we don't know why that is. We do see similar kinds of things, although of a much smaller scale in the simulations as well.
Okay, thanks. I'll think some more about it. Samuli, do you want to ask your question?
Yes, thank you for a very nice talk. Now, this might be a stupid question, we'll see, but I understand that this is a two-dimensional system. But so I was going to ask, can you make it less so, or can you imagine some other system for the purpose of, or modification of these experiments for the purpose of actually playing with the Kelvin wave cascade?
Okay, so let me just start answering. So first, because the talk was short, I didn't give every possible number. So our system in particular, as is conveniently pictured here, has a vertical trapping frequency on the scale of, I think, 300 hertz in this experiment, which is comparable to, but smaller than our chemical potential. So for sufficiently short wavelength excitations, our system is properly 3D. But for the length scales we're probing, it's 2D. And in particular, it's clear the vortices and all the vorticial structure aligns itself sort of perpendicular to the extended direction of the system. So we have a lot of freedom, in fact, with which we could tune the degree of 2 or 3 D-edness of this. If we wanted to go to a bulk 3D system, more like Zoran's group, this technique actually could be applied, but we would have to play a little bit more trickery in order to make localized tracer particles in full 3D space, but it could be done.
Thank you.
Wei, do you want to ask your question?
Yeah, thank you for the nice talk. I very much like the way how you guys inject trace particles in a tiny BEC. So my question is, I think you mentioned that you believe because the vortices can annihilate and disappear, so you believe there is probably a direct cascade instead of inverse cascade.
Yeah.
Is that right?
Yes.
Yeah, okay. If that's the case, I guess you manage to inject energy at large scale by pulling the two laser beams, counter-rotating laser beams. Can you put the two laser beams very close to each other so you inject energy at tiny scale, at a small scale to begin with?
Yeah, so if we wanted to inject energy at short scale, probably this is not the technique that we would use to do it. So I'll give a suggestion of what we might do, and maybe you could say it's not the best suggestion. So what I would probably be inclined to do instead is to have interfering laser beams that make an optical lattice pattern, and then to sort of wiggle that lattice pattern to create highly excited phonons in a localized way. One could also pulse on lattices and things like that. But definitely using lattices, you have the capability of producing relatively spectrally narrow excitations in a BEC. Yeah. So that would be probably my explanation to do what to do.
I see. One very last question is, can you just quench the BEC, create a turbulence by rapid quenching, and then measure the velocity field there? Because then the turbulence could be different. Then you may be able to generate a so-called ultra-quantum turbulence.
So I have a degree of skepticism that could be done cleanly, in the sense that by quenching, I think you meant quench cooling, right? Yeah, so the actual cooling process itself takes a certain amount of time. Right. So what we would do is by some way or the other, move the cutoff in either position or momentum space that is selecting the maximum allowed momentum in the problem, and quickly quench that. So provided that the thermalization time is fast, then I would say the local thermalization time is fast. Then I would say yes, but I would have a concern that there would be an overlapping of timescales in that problem. But we are actually thinking about experiments like that in a different system. Let me go to this one here. So in this Rayleigh-Taylor project, we strongly suspect that this final state that I'm circling here is a spinor turbulent state. We don't have any proof of that right now, but we believe that that's what it is. So in that system, this is a two-component immiscible superfluid system, and in this case, it got turbulent because we did a Rayleigh-Taylor excitation that stirred the whole system up. But we can also do quench analogies in this one, where we prepare the system in a superposition of those two spin states, and the intrinsic dynamical instability will serve as a quench and create what we've observed this. So create quite a complicated and sort of time of sort of relaxing hyperfine structure.
Okay, thank you so much.
All right, I think Zoran and then Ladislav.
Hey, Ian.
Hi, Zoran.
Good to see you. And very nice experiments. I love the tracers. I have a comment slash question. Well, initially it's a comment, and then it becomes a question if you have a comment on my comment. So I think we now have, after years of thinking and getting referee reports and reading, I think we have a sort of inexact rule of thumb understanding that actually all these fluids, both helium and our systems, are, to a decent approximation, incompressible on length scales larger than psi and compressible on a length scales smaller than psi. Now in helium, we would say it's incompressible because there is no length scale shorter than psi. But with our system, it's nice that in principle there's both, right? Because they're both accessible, right? And so I would say, that it all fits nicely together because all our measurements where wave turbulence dominates, and we know from simulations that compressible flow dominates, are well above 1/xi, i.e. in length scale, it's shorter than xi. Whereas your measurements, at least the majority, if I look at the plots where the theory actually works, are all length scales larger than xi, or momenta, less than 1/xi. Now, an additional comment to that is it still depends what you measure, right? So, in principle, you could isolate your perpendicular or longitudinal component of the, of the flow. So even if it doesn't dominate, you could measure the, incompressible flow in the compressible regime, incompressible flow in the incompressible regime. But I think sort of to the first order, to me, it seems it nicely fits that with your nice probe, and also the Australian stuff, which looks at length scales, longer than xi, we expect to see essentially, incompressible physics in our systems. And on short length scales, we expect to see compressible physics.
Yeah, so I guess my response to your comment is that Ming Xu agrees with you, and I haven't verified his calculations. So he, in our simulations, also broke up the flow into the compressible and incompressible part of the flow fields and found that our observations are being dominated by the incompressible part.
Yeah, but that even in the SI of the Navon 2016, we were not interested in that length scale, but we saw that, then we were just trying to show that the compressible does dominate. But as a byproduct of those simulations, we saw that, at short length scales below xi, it was sort of, 2-to-1, 3-to-1 in favor of the incompressible, which was not what we were looking at, but we sort of, we saw that it was there. And in a recent, coarsening experiments, which are all below length scale of xi, so above length scale of xi or below momentum 1/xi, we see that it's also incompressible physics, like in yours.
Yeah, I would be my degree of confidence would be to say my feeling is that I agree with this observation, but I'm not going to say I agree in a strong sense yet.
Yeah, which I think is nice, because in helium they cannot probe those short length scales. We can just do both, but I don't know how to switch the probes. So we actually know, like when we study wave turbulence, where we inject at length scales which are much smaller than at momenta which are much smaller than 1/xi, then it doesn't make sense until it reaches 1/xi, and then it starts matching the wave turbulence theory.
Yeah, so
in fact, it's not even isotropic down there. It's very small K.
Yeah, so I don't know if there's going to be a proper analogy, but as we're starting to play with these spinner systems, for this one, I mean, technically, the healing length in this Rayleigh Taylor was, the spin healing length in this thing was about 3 micrometers, maybe 2. Look at the paper, 2 or 3, which is already a little bit larger than our, somewhat larger imaging resolution. So if this is exhibiting any kind of analogy to that sort of turbulence, we will have better access to this crossover regime. But I'm sort of interested in that more in the perspective of the sort of identifying the source of the viscous loss part of this problem. Like, well, what is the energy extraction part at short length scales? And I think that the spinner system is probably going to be a pretty fun place to look for that type of physics.
All right. I'm done.
Ladislav, do you want to ask your question?
Thank you very much. So first of all, thank you very much for an interesting talk. I have some experience with quantum turbulence in helium, not in Bose-Einstein condensates. But there in liquid helium, I mean, what is essential is just the tangle of quantized vortices. You didn't talk about vortices much in your talk, but anyway, one can estimate how many vortices you have in your system. And it seems to me that you have of the order of 500 vortices there at most. And then, I mean, if we performed experiments in helium-2 with tracer particles, then whether you obtain just the signature of quantum turbulence of the Kolmogorov type or what is called the Winen type depends on the length scale. If you are probing the turbulence at the length scale, which is coupled with the mean distance between quantized vortices, then you are dealing with something which is known as a Winen turbulence. But if you do that at much larger length scales, only then you can have what is known as a Kolmogorov turbulence. And that is connected with the essential fact and essential requirement in Kolmogorov turbulence that you must have a possibility to stretch vortices. And it is not possible to stretch a single quantum vortex. Only in the case that you have many quantized vortices which are partly polarized, which are kind of organized in, say, and bundles, that you can stretch such a bundle, and then you can talk about Kolmogorov turbulence. So I am a little bit puzzled, I mean, what you are talking about when you're in 3 dimensions, and I would like that you comment on that. And I can also add that this depends on the length scale. If actually you measure kurtosis at the length scale, which is comparable with the mean distance between quantized vortices, the kurtosis is greater than 3 and substantially greater than 3. But if you increase, the distance at which you probe the turbulence, then there is a transition towards Kolmogorov turbulence. And then, as in classical turbulence, you get a kurtosis, which is of the order of 3 or closer to 3. If you can comment on that, I would be very grateful. Thank you.
Yeah, so let me sort of start with things that matters of fact that are easy to answer. So firstly, with this experiment, we didn't do measurements of the vortices. So already when I say fact, I'm already going to be referencing simulation. It is important that our system is relatively two-dimensional so that the vortices are aligned perpendicular to the 2D plane. So we don't have a sense of vortex lines anymore. We just have 2D quantized vortices. And that the size of our tracers are such that at all times they should have multiple vortices inside of them. And they're spaced by a distance that is large compared to the intervortex spacing. Okay, so we are, just as a matter of fact, using numbers from the simulation, we are in that kind of regime. But they're not much larger than the intervortex spacing. It's not like there's 1,000 vortices between them, but larger. Okay, so those are just the facts of our system. When we actually sort of wrote the paper, I think if you see the first draft of the paper, I think we titled it Kolmogorov Turbulence and modified it based on referee comments to Kolmogorov Scaling, because of reasons such as this, is that we do observe Kolmogorov scaling behavior, but it is not clear that we can assign the mechanism underpinning this to the Kolmogorov mechanism. And it is, in fact, fundamentally a compressible fluid. The vortices are point vortices, and they can annihilate, and in fact, they can also, at a sufficiently large fluctuation, pairs can pop out of the vortex vacuum as well. So it is, I don't know what connections can be drawn between this and the 3D systems. What I can say is that the simulations for some of the 3D systems, and this is something that probably Zoran can comment on better than me, you can certainly have vortex tangles in those systems. So I don't think that there is inherent contradiction in the capabilities of these, but these are still small systems, so it wouldn't be of the scale that's possible in helium. So that's only a partial answer, I admit, but I think it's the best I can do.
Okay, thank you.
All right. Thank you again for a really nice talk and describing a beautiful experiment. And I think this concludes our quantum fluids webinar series for this round. So hopefully I'll see everyone again in the fall.
Yeah, thanks for inviting me, and I really appreciate the question. So,
You're welcome. Enjoy your thesis defense now.
Oh no, that's at 4 o'clock our time that I have to be on the thesis committee, and your super panic-inducing emails will finally cease.
Excellent. All right. See you later.
Thank you. Bye.